Okay, lecture 31, normal to standard normal examples. So a little bit more what we did last time. You should find these pretty straightforward. I hope you can pause me and just do them. But I'm going to just go ahead and do the very first one. So example, I'm not even going to, I'm just going to jump right into this. We're not going to have some pretense of some experiment or data we're taking from nature. I'm just going to say that B is a random variable. It's normally distributed with mean, 25, standard deviation 8. And I want the probability that B is greater than 40. Okay? Convert to the standard normal. Probability that B is greater than 40 is the probability that, I hope you did this, B minus the mean, 25, over the standard deviation. Work at it and make sure you get it straight, that the mean goes here and the standard deviation goes here. People get that mixed up sometimes. Greater than, it's 40 minus 25 over 8. This becomes the probability that Z is greater than 1.75, right? 1.875. Yeah, 1.875. We've reduced it to a problem we've already seen. By converting it to a Z random variable problem, it's been reduced to something we've already seen. This is one where it's area to the right. I need that area to the right, but the table gives me area to the left, and that's the probability of the complementary event. So we need to do 1 minus the probability that Z is less than 1.875, and that gives you 1 minus 0.9699. So you get 0.0301. Okay, let's see. I want to leave some room here. I wonder if I can squeeze the next one in. So if you had a little trouble there, that should really give you a way to do do the next one. In fact, I'm going to rub out the bottom of this. You have it. If you need it, you can pause it and copy it or whatever. But I'm going to rub out part just so I have enough room right here. So the next one says C is normally distributed with mean negative 50, standard deviation 10. And it says to find the probability that C is greater than negative 63. Okay? Well, that should be the probability of subtract the mean and divide by the standard deviation. So I have to subtract a negative 50, which of course is adding a positive 50, but it's still subtracting the mean, subtracting the negative 50 and dividing by the standard deviation. This magically becomes Z, and this becomes negative 63 plus 50, right? Negative 13 over 10. It's negative 1.3. Again, I want area to the right, so I got to do 1 minus area to the left. And from the table, I get 1 minus 0.0968, so I get 0.9032 is the final answer. Okay, next example. I'm just wanting to kind of fly through these here. D is normally distributed with mean 1250 and standard deviation 175. And you want to find the probability that 1200 is less than D, which is less than 1300. So again, please pause me. This is like a problem we've done before. Once you convert it to Z's, it's like a problem we've done before. Okay, off we go. As before, we'll just all the way across subtract the mean and divide by the standard deviation. I get the probability of, when I compute that, after I simplify it, I get negative 0.29 is the closest I'll be able to get in my table. Less than, this becomes Z, less than 0.29. So that gives me, how do I do the probability that Z is between two values? I could draw the picture again. I'm not going to do that. I want to get the probability that Z is to the left of this one. But I got to stop there, which means I want to subtract off the probability that it's less than that one. If I look that up, I get, where am I? 0.6141 minus 0.3859, so I get 0.2282. So there you go. There's that probability. The last one we have that R is normally distributed with mean negative 1500, standard deviation 17. Want the probability that negative 1520 is less than D is less than negative 1476. I think you should be able to work this through now, so please work it through. Your final answer should be, let's see, I got 0.8017. I think that's right. So you work that through, though. Don't just put dot, dot, dot like I did. Okay, finally, I want to get to something that is very important. Let's suppose, draw a little line here, X is normally distributed with mean mu, standard deviation sigma. I'm not going to say what mu and sigma are, just generically mean mu and standard deviation sigma. I say find the probability that a randomly chosen X value will lie within one standard deviation of the mean. So this is number one. So look, here's my number line, right? And here's the mean somewhere. And what I want to do is I want to find the probability that this random variable's values lie in this interval, right? So I'm going to have, I'm going to have some hump over here, right? That is my bell curve. I want to get that area. That's what I'm asking for. So am I not asking for, look at this, don't I want the probability that X lies between, well, this bigger number here is mu plus sigma, isn't it? And this smaller number here, I went down to sigma, so it's mu minus sigma. That's actually what I'm asking for, isn't it? Let's run through and see what we get. What do? We take this number and we subtract the mean and we divide by the standard deviation. Over here, I take X, I subtract the mean and I divide by the standard deviation. And over here, my number mu plus sigma, I subtract the mean and divide by the standard deviation. The result is, look at this, mu minus mu goes away. I'm left with negative sigma over sigma. I get negative 1 less than, I know that's Z, less than mu minus mu goes away. I get sigma over sigma. I just get 1. Okay, I'm going to leave you to figure out what that is. I got to do the probability Z less than 1 minus the probability Z is less than negative 1, but you should get 0.6826. Do you remember when I said that for a lot of data sets, about 68% of the data value will lie within one standard deviation of the mean? Well, it turns out that if what we're talking about is a normally distributed data set, and many of them are, many populations of data are normally distributed, then I really made a pretty accurate, pretty solid statement that about 68% should lie within one standard deviation of the mean. There you go. Number two, find the probability that we're within 2 standard deviations. So this is what I want. I want the probability that the random variable lies, well, how far up can I go? Mu plus 2 sigma this time. Right out here is mu plus 2 sigma, and back here is going to be mu minus 2 sigma. Okay, so back here another one is mu minus 2 sigma. That's going to turn out to be the probability that negative 2 is less than Z is less than 2. So again, dot, 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 you do the work. Like I just did. Nothing to it. And you're going to end up getting 0.9544. 0.9544. Do you remember when I said if you have a data set, roughly 95% of the data lies within 2 standard deviations of the mean? You can see if we're talking about a normally distributed data set, normally distributed population of data, that's pretty close to true, right? About 95, almost 95.5% lie within 2 standard deviations of the mean. Okay, and so, saying that a random variable lies within one standard deviation of the mean is saying that its z-score is between -1 and 1. Saying that a random variable value lies within two standard deviations of the mean is saying that its z-score lies between -2 and 2. So the z-score really does tell you how many standard deviations your value is away from the mean, above or below. Number 3, I don't think I'll do it, but it's looking for, when I say probability that it's within 3 standard deviations. So I won't even draw it up there. But I'm looking at wanting that, right? And that will be equal to, you can work it through, and not surprisingly, you should get that. And if you work that through, you get about 99.74. Or sorry, 0.9974, right? 99.74% of the data. So 99.75% almost of the data of a population generally lies within 3 standard deviations of the mean. You will recall in the example of the uniformly distributed random variable, the continuous uniform random variable, it didn't turn out that it was 95%, say, that was 2 standard deviations away. If you went up 2 standard deviations and down, you got the whole data set. You got 100%, and then some. It went beyond. So it's still roughly 95%, right? It's actually a little more. But if we're talking about having a bell curve to the data, then typically about 68% will be within 1 standard deviation of the mean, about 95.5% will be within 2, and about 99.75% will be within 3 standard deviations of the mean.